everyone. Welcome to the Rock Online platform. My name is Salim Isiaka. I'm here to be your tutor here. We're to look at some questions in physics. And as we're going to go through the journey, I believe you're going to have a nice class with me. However, do not forget to share, like, and subscribe to our channel for subsequent videos that might benefit you or your loved ones. All right, let's begin. We have the first question here. It says, in a resonance tube experiment, a tube of fixed length is closed at one end, and several tuning forks of increasing frequency are used to obtain resonance at the open end. If the tuning fork with the lowest frequency which gave resonance had a frequency F1, and the next tuning fork to give resonance had a frequency F2, find the ratio of F2 to F1. And we have to ask ourselves the question, what do we use a resonance tube experiment for? We use a resonance tube experiment to get the frequency, the resonant frequency of a tuning fork. We use it to get a tuning fork or that of a sonometer. So let's see how it goes. So we have a lot. There is a length here. It is fixed, but this, take a look at it. A tube is fixed length. It's closed at one end. So if it is fixed, if it is closed at one end, we call it a closed tube, or we call it a closed pipe. If it is open at both ends, we just call it an open pipe. So let's see how it goes. So it always goes like this. I believe this is a tube, something like this. And we have a tuning fork. So tuning fork are used to obtain a sound of different frequencies. And the first resonance will happen when the antinode just coincide with the open end. And you can see at this point, we have the length L. And here, don't forget, there is one thing about this waveform. The distance between this place is like a node, and this is like an antinode. The distance between a node and an antinode is always lambda over 4. Maybe you're afraid how that's happened. Let's quickly take a look at this sinusoidal waveform here. And we say, let a traveling wave be like this. I represent just a traveling wave like this. And we look at another wave that is what? That is moving perpendicular to this wave. And let's superimpose. So we have to superimpose. And we have something like this. And maybe it's going to look a bit sensible to you now. Moreover. So let's break this into two. And what do you see? You are seeing a part of it that looks like having a node here and an antinode at this point. So this is literally what we are having at this same end. So we know that the time taken or the distance traveled by a complete circle is known as what? Wavelength or lambda. So that distance is, if you take a look at this, from here to here is half, from here to here is another half. So from here to here, if it is half, then from here to the middle will be the what? Will be the quarter of the whole of the wavelength. So we're going to say L equals to lambda over 4. That is the first point of resonance that will happen in the what? In a tube. And here L equals to lambda over 4. What do we come up from there? So we are going to say that definitely then lambda equals what? 4L. If you cross multiply, you're going to get lambda equals to 4L. And there is a popular equation, which I believe you must have known, which is the equation that relates every of waves to each other. And that is just what? A relationship between velocity and what? Frequency with what? Wavelength. So V equals to F lambda. So we have lambda to the 4L. Definitely V equals to what? 4F times 4L. Then we are thinking of frequency. Don't forget our interest is in the frequency. So we make frequency the solve a formula. I have F equals to V over 4L. This is the first frequency that you can get a sound that makes the loudest noise or pitch in the what in this tube, and then we call it what the fundamental frequency, which in this case we are not calling it F naught because the question says F1, so we're literally going to change the naught to 1. So this is the formula for what F1. Is that fine? So let's go for the F2. The next resonance will take place when a circle is nearly completed but it opens at the amplitude. So let me draw a system of the second resonance. So this is the first resonance. Let's go for the second resonance. Let me quickly draw that here. And here I'm going to have it as and that is it. So this is the position of the second resonance, and you can see it's still the same length of tube. So we see going down to all right. The same way, let's take a look at this. Obviously, there is a little synonymity with the two of them, because if you try to turn this by an angle 90 degree, you most likely are going to have this picture. Just ask yourself, if I turn this down by 90 degrees clockwise, what do I get? Something like this, right? Obviously. So let's see what we're going to have. We have this one up to here, which is here. Then we have the other parts up to here. It's like from here to here, that's what we're having from here to here. And what happens? Don't forget to say that from here to here is lambda over 2. From here to here is what? Lambda over 4. So we add them up. We're going to have what? L equals to lambda over 2. That's the distance between here and here. Then plus lambda over 4. Lambda over 4 between here and here. Just remember the same thing we said. This was going to be what? Lambda over 4. So let's add it together. We are going to come up with L equals to 6 lambda all over 8. If I'm right? Yeah. 6 lambda all over 8. Or you want to break it, you say L equals to 3 lambda all over 4. Here, definitely, we can say, let's do what? Let's cross multiply and make lambda the Fourier formula. So the wavelength at which the second resonance will take place is going to be 3 lambda equals to 4L. Then lambda equals to 4L all over 3. That is the wavelength at which the second resonance will take place. Now we go back to the original formula, which we already said we've already used. Now it means that what? The velocity of sound doesn't change no matter what the resonance you are doing. So velocity of sound isn't going to change. So we're going to have V equals to, we come now, F, the same F, but this time around to make sure we are not mixing it up with the first resonance frequency, we call it what? F2, according to the question. It says the next tuning fork to give resonance had F2. So that is the second resonance now. And we're going to multiply it by what? Our wavelength, which is what? 4. We're going to multiply with our divided by wavelength, beg your pardon, and that will be what? Times 3 all over 4L. I believe you understand that, and that is going to be V equals to 3. Then we're going to get F2. All right, so my bad. We go again. Lambda is already 4L over 2, so multiply by 4L all over 2. And with that, we have F2 equals to what? 4L over 3, beg your pardon, is going to be 3V all over 4L. And now we have the what? F2. Yes, that is F2. So the ratio F1 to F2 now is what we have to show. Now let's carve out a space there to get our ratio F1 to F2. Oh, rather, it is F2 to F1. So F2 all over F1, we had F2, which was what? 3V all over 4L, all over, what was our F1? V all over 4L. And here we're going to say it is same thing as 3V all over 4L multiplied by 4L all over what? All over V. All over V. We are going to reverse this, so it's going to be over V. L cancel L here, 4 cancel 4 here, and V cancels V. What are we left with? At the numerator level, we are going to have what? 3. At the denominator level, we are going to have what? 1. It means it's going to be 3. Obviously, 3 over 1 is 3. So the correct option here is going to be what? B. Right, let's go to the next question. All right. The question says, which of the following is not a vector quantity? Which of the following is not a vector quantity? We know what vector quantity is. Vector quantity is a quantity that has both magnitude and direction. And the reverse case is a scalar quantity. That is a quantity which has only magnitude but no direction. Let's take a look at the following options. The first one is force. I believe your physics teacher, your first time in your secondary school physics, you were told that force is always a vector quantity. So this is not going to be a problem. Force is a vector quantity. Altitude. What is altitude? Altitude means height. Altitude means height. So if you are thinking of height, you can only say the height is 3 meter, 4 kilometer, 500 centimeter. You wouldn't tell me the height is 3 meter in south. It doesn't really make a sense. It's only, you say that only if you are doing what? If you are talking about what? Displacement. So altitude is obviously not going to be what? A vector quantity. So it is an option that is correct. But let's take a look at the remaining options. C, we have weight. Weight and force literally means the same thing, only that's what? Where force goes with acceleration due to gravity. When weight goes to acceleration due to gravity, force goes for just acceleration. Displacement, yeah, is very similar to distance, but displacement takes in account with what? The direction. So it's also what? An vector quantity. So acceleration is also what? A vector quantity. So the correct option is B, altitude. Next. All right, question 3. The question 3 says, if the relative density of a metal is 19, what will be the mass of 20 centimeter cube of the metal when immersed in water? So we know this is a topic from pressure density, relative density, flotation, and the Archimedes. So let's take a look at the parameters we're given. So we're given that what? Relative density is equal to what? Is equal to 19. And we're given that volume equals to 20 centimeter cube. However, we know that what? The relative density is equals to density, or rather, density equals to relative density times what? Density of water. So relative density, it implies that density of metal, the metal given to us, is equal to relative density times density of water. However, there are two values for densities of water. One, we have the value in CGS system, that is what? 1 gram per centimeter cube. That's the density of water. Or the MKS system, we have it as what? Density of the same water is what? 1000 kilogram per meter cube. Since our value was given to us in centimeter cube and our options are given to us in gram, why do we have to go through kilogram or meter cube? So we just have to go with CGS system. How do we go about that? We get the relative density of the metal, density of the metal, which is going to be 19 times 1. And that is what? 19 gram per centimeter cube. And don't forget, the density is same thing as mass over volume. And this is going to imply that I can have my density, or my volume is going to be, or rather my mass is going to be density times volume. So this is going to be, it means that my mass is going to be 19 times 20. And this is what? 380 what? Gram. Don't forget, it will be in what? In gram. However, you are most likely to be tempted to look at something The last set of words they use in the question might be tempting. Let's take a look at the words. It says of the metal when immersed in water. When immersed in water. So, do we have a problem with mass when the body is immersed in water? Obviously, no. The problem comes when it has to be what? Weight. Because according to Archimedes' principle, when a body is fully or partially immersed in a fluid, it displaces an amount of fluid equal its weight. So it doesn't say equal its mass. So we're not going to think of an apparent loss in mass. So our option is strictly going to be what? Our 380 grams. So the answer there is what? A. Next. So we have question 4. Question 4 says, given three capacitors, 0.3 microfarad, 0.5 microfarad, 0.2 microfarad, the joint capacitance when arranged to give minimum capacitance is what? And this question is a bit tricky. But before we go into digressing the question, let's ask ourselves, what is a capacitor? Capacitor is a component used, an electrical component that is used to store electrical energy. However, it's not the only electrical component that stores electrical energy. We have inductor and we have some accumulators. However, one special thing about capacitor is that what? It stores electrical energy in form of what? Electrical field. It stores it in form of electrical field, and that's the one thing that is spectacular about what? About a capacitor. If it were to be an inductor, it stores it in the magnetic field. If it were to be an accumulator, to store it in form of what? Chemical energy. Let's take a look at it again. Now, the arrangement of capacitors, to give us minimum, we can arrange it in two ways. We can arrange a serial arrangement, or parallel arrangements. However, one thing that is special about capacitor is that they behave just in opposite way of resistor. So resistors will give you maximum resistance, maximum total capacitance resistance when the what? When they are arranged in what? When they are arranged in series. However, the reverse is the case for what? For capacitor. So for capacitor to give you minimum, look at that word minimum. It means that we must arrange the capacitors in what? In series. If we want to get the maximum, then we arrange it in what? In parallel. So let's have a capacitor, the first capacitor, the second capacitor, and the third capacitor. So we are going to put the values respectively: 0.3 microfarad, 0.5 microfarad, and 0.2 microfarad. Don't be tempted to add them up, because if you add them up, it means your arrangement was in parallel and it's going to give you a higher value. So let's see how it works to give us a minimum value. In this case, it's going to be what? 1 over C total is going to be 1 over C1 plus 1 over C2 plus 1 over C3. And here we put our respective values there. So 1 over C total is going to be 1 over 0.3 plus 1 over 0.5 plus 1 over 0.2. And we go. What do we have there? Obviously, we bring out our calculator and we can say 1 over C total equals 1 by 0.3. This is 3.33. Let's use 2 decimal place, plus 1 over 0.5. That is going to be 2, plus 1 over 0.2, and that is going to be what? That is going to be 5. So our total capacitance there is what? 1 over C total equals to, obviously this is going to be 7, so it's going to be 10.33. However, this is just 1 over C total. It's never C total. So get C total, we do what? We take the inverse of both sides. So it means C total is going to be 1 over 10.33. And that is going to be in what? Microfarad. Let's take a look at the answer. 1 by 10.33. So the answer is going to be 0.097 microfarad. And Approximately, we can say it is, since there is no 0.097, we are going to use what? 0.1. That is the approximation of that. So here, C total is approximately going to be 0.01 microfarad. So the correct option is going to be C. Let's go for the next one. All right, question 5. A ship traveling towards a cliff receives the echo of its whistle 3.5 seconds. After 3.5 seconds, a short while later, it receives the echo after 2.5 seconds. If the speed of sound in air under the prevailing conditions is 250 meters per second, how much closer is the ship to the cliff? And this has to do with what? Echo. Echo. So when you get a question, you try to get the topic from which it is coming from. It's about echo. We say echo is a reflection of sound. Whenever a sound is traveling, it hits a barrier, bounces back. Just the same way light travels and hits a barrier and reflects back, sound also does that. So let's see how to solve this problem. And we go. So we have a ship. And one thing formula about there is this popular ideology that before, see, let's say this is a ship and this is a barrier that is bouncing back the sound wave towards the ship. So if the sound wave travels, it will hit the what? It will hit the barrier. And before this person in this ship will hear the sound reflected back to him or her, it must have traveled another distance. So the first distance is d, the second distance is d. So the total distance the sound wave travel is going to be what? D plus d, which is going to be what? 2d. So literally we're going to say velocity is displacement over time, which is 2d all over c. This is the formula for what? Echo. And here we told that what? If the first whistle was heard 3 seconds after. So our time is 3.5 seconds. And we know that the question gave us the what? The velocity of sound, which is v, and it is what? 250 meter per second. So let's get the first distance at which this happened. It's going to be what? D equals to Vt all over 2. If you cross multiply, you divide by 2, you're going to get that. And this is going to be Vt 250 times 3.5 all over 2. And this is obviously 125 multiplied by 3.5. Let's see how that works. And here our answer is 437.5. So the first distance is 437.5 meters. So the ship was actually in the first instance was 437.5 meters away from the cliff. However, it was moving towards the cliff when the second echo was sounded. This time around, it bounced back in what? In just 2.5 seconds. So let's call this one the D1. And to get D2, we see the same formula because the question says the prevailing condition is 250 meters per second. So the speed of sound in here doesn't change. So we say D2 is going to be what? V times T2 all over 2. That is going to be what? V, the same 250, but this time around times what? 2.5 all over 2. And here we get the second distance, and this is going to be 125 times 2.5. And my answer is 312.5 meter. Then the question says, how much closer is the ship to the cliff? How much closer is the ship to the cliff? We don't have to worry about anything again. We just look at what? The difference between the first distance and the second distance. That's how much closer it is. I don't know if you understand. So it's going to be D1 minus D2. That is going to be 437.5 minus 312.5 all in meter. And that is going to be 437.5 minus 312.5, and is going to be 125 meters. So our answer is going to be 125 meter. So the correct option there is option B. Next, we have a piece of wood and it's floating on water. The forces the forces acting on the wood are what? We have a piece of wood and it's floating on water. What are the forces acting on the wood? And the question might trigger some response. Oh, there is always one force that is supposed to act on anybody floating on water. That is going to be what? Weight. However, the wood is not submerged, it is floating. So, and the question says the forces acting on the wood, not on the water. So the forces acting on the wood are just what? Obtruse forces and what? And viscous force. Obtruse force and viscous force. However, let's see the options. Obtruse and reaction. Reaction also means what? Weight. Weight and reaction, they mean the same thing. So we are cancelling weight out of the possible answers because it says acting on the wood. If it had said acting on the water, we would have considered what? The weight of the floats. So of the wood. So the next option says weight and obtruse. We will not take weight. Weight can never be in that option because it's the wood. So the next one says obtruse and what? Viscosity. And obviously that is the correct option. And the last one is weight and viscosity. We don't consider weight because the question did not say on the water, it says on the wood. So next, so the correct option here is D, obtruse and viscosity. Next, a force of 16 Newton applied to a 4.0 kilogram block that is at rest on a smooth horizontal surface. What is the velocity of the block at time t equals to 5 seconds? So we're looking at the relationship between force, mass, and what? And velocity. However, directly you know that they might not really have a direct relationship, but at the same time they have an indirect relationship. Since acceleration has to do with velocity, let's take a look at how to approach this problem. So we have a force F, and F is given as what? 16 Newton. And the mass of the body is 4.0 kilogram. That is at rest. It was at rest on a smooth horizontal surface. The fact that they use what? Smooth horizontal surface means that what? We should neglect friction. So friction is out of the equation because it is smooth. If it's smooth, no friction. Let's go. What is the velocity? We're looking for velocity equals to question mark. And time t equals to what? 5 seconds. However, force equals to what? According to our second law of Newton's second law of motion, says the time rate of change of momentum is directly proportional to the what? To the applied force and takes place in the direction of the force. So F equals to mv minus u all over t. That's with this, we're going to get the velocity. However, do we have u? No. But at the same time, we have it because the question says rest, rest, rest. In physics, when we say something is at rest, we mean the initial velocity is nothing, it's actually zero. So literally, we have what? U equals to 0 because the body is what? At rest. Whenever a body is at rest, initial speed is going to be 0. So here we can use the formula 16 equals to mass 4 into v minus 0 all over 5. And we can cross multiply. We have 16 times 5, and that is 80 equals to 4v. And divide both sides by 4, we're going to have our v, and v here is going to be 20 meter per second. And that should be option C. Next. If the normal atmospheric pressure in a laboratory supports a column of mercury 0.76 meter high, and the relative density of mercury is 13.6, then the height of water column which atmospheric pressure will support in the same laboratory at the same time is what? This question has to do with what? With pressure. Pressure at any place on the surface of the earth. If the altitude from the sea level is the same, then we are going to observe the same pressure. And that's the principle by which your popular YouTube manometer was designed by. Let's take a look at how to solve this. Alright, so the normal atmospheric pressure in laboratory supports a column of 0.76 meter of mercury. So height of mercury is Ag, is 0.76 meter. We have the what? The relative density of mercury. Relative density of mercury is 13.6. So I know you must have known the relationship between relative density and density now, because density is what? Relative density times 1000 in what? In MKS standard. If it is in CGS standard, we use times 1. So it's going to be, it means that density of mercury is going to be 13.6 times what? 1000 kilogram per meter cube. And this is going to be 13600 kilogram per meter cube. That is density. We just did nothing to me. We've not done anything. We only got density from relative density by merely multiplying by 13.6. Let's now approach the method, the problem. Don't forget that what? Pressure is equals to density times G times height. So we need to get the pressure of on mercury. If you get the pressure of mercury, we can move that to get the pressure that will happen to water. So let's go. Pressure of mercury, Hg for mercury, is equals to the density of mercury, which is what? 13600 multiplied by 10 multiplied by what? H, which is what? 0.76. And here we need to have an answer. 13600 multiplied by 10 multiplied by 0.76, and that is what? 103,360 Newton per meter squared. If you like, you can use Pascal. Pressure can be measured in Newton per meter squared or Pascal. However, this is the same pressure that will be supported for water. So we are literally going to look for that of water. So this pressure of mercury will be the same thing as what? Pressure on H2O, water. So this pressure, it means that for water is going to be density of H2O times G times height of H2O, which is the bone of contention. That's what we are looking for. I believe you understand that. We just need to know that the pressure at this in the same place is going to be the same for whatever thing that is inside that place. So we're saying that what? 103,360 equals to density of water is 1000 multiplied by 10 multiplied by what? The height of H2O. And this is going to be, it means that what? My height of what? H2O, height of H2O, height of water is going to be my pressure 103,360 Pascal all over 10,000, and this is going to give you what? 10.336 meter, and that is approximately 10.3 meter. That is option B. So our answer is height of water is going to be 10.3 meter, and that is the correct option. B is the correct option for question 8. Before we move to the next question, are you subscribed to us? You have to do that, please. That's the only way you can help us to help you more. Subscribe, like, and share to your friends and loved ones. Thank you as you do that. Let's go to the next question, question 8. Question 9 rather. The specific latent heat of vaporization of a substance is always, so you need to know what specific latent heat of vaporization of a substance is. The specific latent heat of vaporization of a substance is the quantity of heat required to completely vaporize the substance from the liquid stage to what? To the vapor stage, or you call it the gaseous stage. So the first option says is less than its specific latent heat of fusion. Don't forget, we have one thing that is sure. Anytime you talk of specific latent heat of vaporization, is always greater than the specific heat capacity of that substance. The next one is greater than its specific heat of fusion. First one is less than the specific latent heat of fusion. The B is greater than its specific heat of fusion. C equal to its specific latent heat of fusion. The last one says all of the above depending on the nature of the substance. E, none of the above. As a matter of fact, is always greater than the specific latent heat of fusion. Specific latent heat of fusion is the quantity of heat you need to change a body from the solid state to what? To liquid state. Because of the little separation of intermolecular force of attraction between a solid and when you convert them to liquid is always less than when you want to move it from the what? From the solid, from the liquid state to what? To gaseous state. Obviously, the best option is what? Is always greater than its specific heat of fusion. Question B. Next question. Longitudinal waves do not exhibit. Longitudinal waves do not exhibit. So we need to know what longitudinal waves are. We have two classification of waves, both based on the what? On their modality of transportation or the mode of what? Of movement. We have the transverse wave and the what? And the longitudinal wave. In transverse wave, the wave is moving in perpendicular direction to the energy producing it, whereas in longitudinal wave, they move in what? In parallel or in the same direction with the energy producing it. And they say they do not exhibit which of the following? Refraction. What is refraction? The changing of the direction of a wave when it changes its what? Its medium of movement. B, reflection. What is reflection? It is the bouncing back of a wave when it encounters an obstacle along its way of propagation. C, diffraction. What is diffraction? Diffraction is spreading of wave whenever it moves out of a constriction. The next one is polarization. What is polarization? It's actually making a wave to go in a particular what? A direction. The E is refraction. Refraction is a region of what? Of low pressure or low energy in what? In the motion of a what? Of a longitudinal wave. So as a matter of fact, every longitudinal wave do not exhibit polarization. They do not exhibit polarization. So polarization is the option we are going to choose. So no longitudinal wave undergoes polarization. The only waves that go through polarization are what? Transverse wave, such as light wave or water wave. Next question. The above shows an inverted U-tube with the open end O of one link below the level W of the water in a tank. In order that water should be given to flow from the tank, it is necessary that what? You can see this setup. Just take a look at the setup again. We have some, containing vessel that has some fluid in it. We now have a pipe that is looking like a U-shaped pipe, and it is inverted in the what? Or it is deep into the liquid, and we have some levels. The level of the liquid W, the level of the pipe in the liquid O, and the level of the pipe outside the liquid P. So what do you bring of this? For any flow to happen in this system, definitely, as a matter of fact, it's either you apply pressure at P to draw out the what? The flow, because there is no pressure difference, there is no height difference. For this to happen, it's either you apply pressure at P or you make sure that what? P is below O. P must be what? Below O and W. So let's take a look at the options. The U-tube is completely filled with water and P should be higher than W. If P is higher than W, there will be no flow unless a pressure is applied. Just take a note of that. B, P should be lower than O and W. Yes, like I just said. Only if P is lower than what? O and W, that is when there will be a flow of fluid. All right, next question. Question 12. For a concave mirror to form a real diminished image, the object must be placed where? So we need to quickly take a look at what happens in different positioning of what? Of our concave mirrors. We need to know what happens in the what? In their various positions. So let's quickly take a look at our concave mirror. And don't forget, our concave mirror are also called what? Converging mirrors. So they help to convert rays into a focal point. So let's quickly take a look at how it works around. So we're going to change the various position and see which position will give us the set objective or set conditions for us. Let's take a look. We have what we call a line that is known as the principal axis, a line that is just passing through the pole of the what? Of the mirror. So this is the concave mirror, and we can have a focal length F, and we have a center of curvature C. So let's take a look at how we can the various places our images can be, and the different the various places our objects can be, and the different images is going to give us. So let's take a look at the first one. That's just between the what? Between the pole. This is the pole of the mirror and the what? And the focal length. Let's take a look at that. It will go. There will be a ray that will move from what? From the image, from the object rather, and bounces back. It must pass through the what? The focal length. That's the first thing. And the next thing is that what? There will be an what? An a ray that will move from the curvature down to the what? Down to the head of the image. So we draw a line, and let's see where they are going to meet. And what do you see here? You're going to see that they are meeting at the back of the mirror. And anytime they are doing this, you say the image formed is what? Is not real. So anytime the image is formed at the back of the what? Of the mirror or lens, we say the image is not real. So we call it a what? A virtual image. That's the first thing. Next, however, you can see that although it is virtual, but it is magnified. You can see the final image is bigger than what, or is taller than the what, than the original object. So let's take a look at the second condition. We could put it between what? Between, let me draw another one here. And this time around, we're going to put it between the focal length and the what? And the curvature. So let's put an image here, anywhere here. And let's see how it works here. So I draw this, and it must reflect back through the focus, and there will be a ray that will pass through this until they finally do what? Meets. And you can see they are going to meet down here, somewhere here, and it's giving you an inverted but magnified what? Magnified image. That's the second one. And the last but not the least is what? Is when we put it just after the center of curvature C. Let's see what happens here. We have this. We have our focus, our curvature, and we're going to put it at somewhere after the curvature. And we draw the ray diagram again. And this will pass through the focus. And what happens? It will just be like this. And what do you see happening here? It is what? It is inverted. However, it is what? It is not really going to be diminished. So for a concave mirror to form a real diminished image, the concave mirror is going to form a real and diminished image. You can see this is inverted, so we're going to forget that one. This one is inverted also, we're going to forget that one. This one is what? Is upright, but it is not what? It is not real. It is not real because it is forming at the back of the what? Of the mirror. So it is virtual. So the object must be placed where? Behind the mirror. This behind the mirror, somewhere here, and I'm afraid that will not work. It will not even show. Between the mirror and in focus, we've done between the mirror and the focus. And the image we are having is what? Is a virtual image that is even what? That is even a bit magnified. Between the focus and the center of curvature. Between the focus and the center of curvature, that was what we had there. Between the focus and the center of curvature, and you can see it is inverted. It is not going to be real, but what? Inverted. So in this case, it is not going to be an option. Let's see at the center of curvature. Now let's take a look at what happens at the center of curvature. So we've not put that there. Let's see if we put at the center of curvature. Let's just get what is going to happen. All right. So let's say this is my focus, and this is what? This is my center of curvature. Just at the center of curvature, let's have an image. And let's go. And what? We're going to have this. And we're going to have what? This. And what happens? It's going to give you an image that is what? That is real. That is what? Real. But this time around, it is what? Diminished and what? Inverted. So hopefully that is going to be the only time we have the real diminished what? Image that is at the what? At the center of curvature. That is going to be the what? The correct option D. Question 13. The unit of quantity of electricity is called what? The unit of quantity of electricity is called what? You might most likely to be tempted to choose the first option, which is the ampere. However, it is not. It is coulomb that is the unit of what? Of quantity of electricity. So the answer is going to be what? The coulomb. C is the correct answer for that. Next. The resistance of the wire depends on what? So the resistance of the wire depends on what? The length of the wire, the diameter of the wire, the temperature of the wire, the resistivity of the wire, all of the above. Let's take a look at each of the options. Generally, there is a formula that will give you the solution to all of this problem. It is just what? R equals to rho L all over A. So this will solve at least three of the options, will help us to see how it works. The resistance of any conductor R is a function of resistivity rho, L length, and area A. So the length of the wire is a function of the resistivity, or rather you say the resistivity is a function of the length of wire. So option A is correct. B, the diameter of the wire. However, you might likely to be poised into do what? To be tempted into picking that as going to be your original or the correct option, for which is not going to be. However, let's take a look at it. When you talk of area, the wires are what? Are circular in shape, or they are circular or cylindrical in shape. However, area is a function of diameter. So don't forget that your what? Your area is pi d square all over 4. So it also depends on the what? On the diameter. So it is also a very good option there. Next, the temperature of the wire. For every conductor, the temperature changes. As temperature increases, the resistance of that conductor does what? Increases. Increase in temperature increases the resistance of a conductor. But if it is to be a semiconductor, increase in temperature will rather help its conductivity. So we say for a semiconductor, increase in temperature will reduce the what? Will reduce the resistance. So for a pure conductor, a wire is a what? Is a pure conductor. So we're saying that what? The temperature of the wire also affects the resistance, because the higher the temperature of the wire, the higher the resistance of that wire. The last one is what? The next one is what? The resistivity of the wire. You can see from this formula, resistance is directly proportional to what? Resistivity. So it's also an option. So the best option is all of the above. E is the right option. Next. Two cells, each of EMF 1.5 volts and an internal resistance 20 ohms, are connected in a parallel, or in parallel rather. Calculate the current flowing when the cells are connected to a 1 ohm resistor. So we have two cells that have internal resistance of what? Of 20 ohms. No, sorry, I think that should be 2 ohms. Beg your pardon. It's not 20 ohms, it's 2 ohms. So let's quickly look at how it works, since they are connected in what? In parallel. So let's connect ourselves in parallel and see how it works. So cells can be connected in parallel or in what? In a series. So cells connected in parallel looks like this. So these are the cells that are connected in what? In parallel. And their EMF is 1.5 volts. 1.5 volts. However, their internal resistance are 2 ohms. So the internal resistance, small letter r, is always 2 ohms and 2 ohms. Then they are connected in parallel with what happens. They are connected in parallel. Calculate the current flowing when the cells are connected to a 1 ohm resistor. So there is a 1 ohm resistor that is now here, 1 ohm, and we have to look for the what? For the we have to look for the current flowing. Current flowing. So I is the current flowing. Now, the total EMF here, when two cells are connected in parallel, the total EMF is just one of the two. So you don't need to add them together. If they are connected in series, you add them together. If they are connected in parallel, you just pick one. Don't forget that. So our EMF, effective EMF, is going to be what? 1.5 ohms. And what happens? The total resistance is going to be what? The total internal resistance, R small letter RT, is going to be what? These 2 ohm in parallel with these 2 ohms. And you know when two resistors are in parallel, the answer, the total resistance it gives you is what? Is the reciprocal of the addition of the reciprocal of the individual resistances. So to get R theta, we say is what? 1 over 1 over R1 plus 1 over R2. That is simply 1 over the first resistance plus 1 over the second resistance. And this is going to be 1 over 1. And this is simply what? 1 ohms. So the 1 ohm is the total internal resistance of the two cells. So however, this 1 ohm is now connected in series with another 1 ohm. So we say our R total here is going to be RT plus our R, which is 1 ohm plus another 1 ohm. And this is going to be what? 2 ohms. Now that we've gotten that, we know that our total EMF is what? 1.5 volts. But don't forget from Ohm's law. Ohm's law says that what? EMF is equal to the product of current and what? And resistance. So with that, we can say E equals to IR total. And here I equals to E over R total. And this is going to be 1.5 all over 2. And this is going to be 0.75 amps. That's the correct option. So option A is the correct option. However, apologies for the change in the what? In the unit. It's supposed to be amps and not ohm, because current are measured in what? In amps and not ohm. So the right option is what? 0.75 amps. That is option A. So let's look at question 16. It says, which of the following properties of matter cannot be utilized for temperature measurements? Which of the following properties of matter cannot be utilized for temperature measurements? A. Length of liquid column. B. Volume of a gas at a constant pressure. C. Pressure of a gas at constant volume. D. Resistance of a metallic wire. E. Current produced in a photoelectric effect. Now, the question is asking us which of the following properties of matter cannot be utilized for temperature measurement. So if you look at this, we know that what? A length of a liquid column, if a column, if we have the a column, a liquid that can do what? That can expand appreciably, like mercury, then we can actually use it to do what? To measure temperature. So A is not a problem. B, volume of a gas at constant pressure. So you have what you call what? All your liquid in glass thermometers, they take volume and they increase it at a constant pressure. For instance, your alcohol in glass thermometer and your mercury in glass thermometer, they take advantage of this option B. So it's not a problem. Let's go to the next option. C, pressure of a gas at constant volume. So that is the basis for which a pressure thermometer is designed. So it's not a problem. B, resistance of the metallic wire. That's the basis for which resistance thermometers are also designed. So it's not a problem. E, current produced in a photoelectric effect. What is photoelectric effect? Photoelectric effect is the process by which an electron leaves the surface of the plate when it is being incidented by what? By a light wave. So this, it only has one thing that has to give us this electron to be liberated from the surface of the plate, and that is what we only need one thing. According to Einstein and what and Planck, they say that we only need the frequency. If we get the frequency, we don't have a problem with it. So if the temperature of the incident ray is hot or is high, it doesn't affect. Once we get the so-called threshold frequency, which is minimum frequency for this electron to be emitted, then everything is fine. So we cannot utilize E to do what? To design our thermometer. So the correct option is E. Next. 17. Which of the following is a correct explanation of the inertia of the body? Which of the following is the what? Correct explanation of the inertia of the body? You ask yourself, where is inertia coming from? Inertia is coming from what? From the first law of Newton, the first law of motion, which says that everybody continues in a state of rest or of an accelerating motion unless it is being compelled by an external force. You remain seated forever unless you are forced to stand up, and you keep moving, you remain moving forever unless you are forced to sit down. That's what inertia is telling us. And now let's take a look at the question again. Which of the following is the correct explanation of the inertia of the body? How do we explain? Let's go to the options. The first one, ability to overcome the earth's gravity. Inertia has nothing to do with gravity, so it's not an option. B, reluctance to stop moving. Is it only to stop moving? No. So we're not going to go for that option. However, it's part of the conditions for inertia, but it is not the sole condition. So we go for the next one. Readiness to start moving. Wow, it's also part of the condition. However, it is not the sole condition. The next one, D, reluctance to start moving and its readiness to stop moving once it has begun to move. Look at the word readiness. It has to be reluctance in both cases. So we cannot go for option D just because of the word what? Readiness. Let's go to the last one. Reluctance to start moving and its reluctance. You can see now it's coming. It has to be reluctance. So reluctance to stop moving and reluctance to stop moving once it has begun to move. So option E is the correct option. Next question. Cathode rays are, what are cathode rays? You are most likely to be like you are hearing it for the first time. However, let's see what happens. How do we get a cathode ray? The scientist J.J. Thomson, in one of his experiments, he discovered that when he reduced the pressure of a gas in a glass tube, he saw some mass movement of some particles moving from the cathode down to the anode, and he called them. He never knew what it was. He had to call them cathode rays. From seeing that, these things are moving from the cathode down to the anode. So he literally called them cathode ray. However, he noticed something, that when they got to the anode, they were scintillating, they were sparking, they were glowing. He couldn't explain that. However, when this man Nelbor came up later, he had to explain to us that this was as a result of the excitation. That when an atom or an ion de-excite, it radiates or glows or scintillates. However, if it is the other way around, if it gets excited, then it's not going to do what? It's not going to radiate. So they are high energy electromagnetic waves. However, cathode rays are not electromagnetic waves. Cathode rays are not electromagnetic waves. X-ray are electromagnetic waves. So don't miss that. It's not an option. B, protons. They are not protons. C, stream of electrons. Which is that? Just wait. Let's get the next option. Neutrons. They are not neutrons. E, radio waves. They are not radio waves. So we go back to the option we jumped. That is option C. Streams of electrons. Eventually, when J.J. Thomson finally discovered that, you might likely be asked, who discovered electron? It was the same J.J. Thomson that invented this cathode ray in his cathode ray experiment. Eventually, he was able to get that there are some subatomic particles above atomic level, and he called them electron. That is why that was the beginning of the flaws of John Dalton's theorem that told us that the smallest you can get from an element or an atom or a substance is an atom. However, J.J. Thomson was able to tell us that we can have some subatomic particles such as electrons, and they were moving just from the cathode down to the anode, and that is why we call them cathode rays. So they are literally stream of electrons. Let's go to the next question. 19. A device that converts sound energy into electrical energy is what? A, the horn of a motor car. B, an AC generator. C, a microphone. D, telephone earpiece. A, loudspeaker. Let's take each of the options one after the other. The horn of a motor car. If you press the horn of a motor car, you are sending what? Electrical energy into the horn, and it will give you what? It will give you sound energy. So it is electrical to sound. However, it says sound energy to electrical. So we don't need horn, because horn works on what? On converting electrical to what? To sound energy. B, an AC generator. An AC generator we give it mechanical energy, and it gives us electrical energy. So it converts mechanical energy to what? Electrical energy. C, a microphone. A microphone, when you speak to a microphone, you are giving it a sound energy. And what happens? It converts the sound to electrical signal, and it takes it through the diaphragm of the what? Of the speaker. And when it gets to the diaphragm of the speaker, what happens? It changes the what? The electrical signal back to what? Back to sound signal, and you can hear that. So it is actually the right option for what? For the question 19. So C is the right option, a microphone. However, we wouldn't just drop the remaining options. Let's do justice to the remaining options. Option D says the telephone earpiece. The telephone earpiece takes what? It converts electrical energy to what? To sound energy. It converts electrical energy to sound energy. It's as good as what? As your speaker. So the last one is the loudspeaker. So both D and E literally mean the same. So they are out of the equation. So the right option is what? A microphone. It converts what? Sound energy to electrical energy. Next one. Question 20. Which of the following? The first statement says alpha particles. Second statement says protons. Third statement says neutrons. Fourth statement says beta particles may be found in light nuclei. What are light nuclei? Light nuclei are just nuclei that are not heavy. For instance, your oxygen, your nitrogen, your hydrogen, they are light nuclei. But when we say heavy nuclei, we mean cobalt, uranium, thorium. So they are heavy nuclei. And when you have heavy nuclei, something is most likely to happen. We will not tell you that. We're going to get to something that happens when we have heavy nuclei. But for light nuclei, they all are going to get protons at the same time. They are going to get neutrons, because we know that every atom or every element has proton. They have what? They have neutron. However, when it comes to the alpha particle, if it is not a radioactive element, it's not going to give you what? An alpha particle. The same way for beta particle. So the right option is what? 2 and 3. That is option D. Next. All right, we have a circuitry here. Let's take a look at that. Question 21. In the diagram above, X and Y have resistances 40 ohms and 60 ohms respectively. If power dissipated in X is 10 watts, then power dissipated in Y is what? So this question, we have to calm down to solve the problem. So we draw the circuitry. Let's take a look at the drawing. Alright, so we have the circuitry. We have the first resistor, the second resistor. They are connected in parallel, and you call the first one X, you call the second one Y, and you have 40 ohms, you have 60 ohms, and they are connected to some cells, some battery rather. Single one, you call it cell. When they are more than one, you call it battery. So they are battery. So we're told something. Only one thing we're told again after this. We're told that the power dissipation in X is what? 10 watts. So the total power here is what? Is 10 watts. But what is power? Power is what? Power is, in terms of resistance, we can say it is what? Current times resistance. But it is not current times resistance, but current squared times resistance. Say P equals to I squared R. So this power for the X, power of X, is current through X times resistance through resistance of X. So I can literally change it to what? I power at X is equal to I squared X, where X is the resistance. So Let's take a look at that. It means that what 10 equals to I square. I don't have the current. I just want to get the current that goes through what? That goes through the X resistor. So I squared times what? 40. So I squared equals to what? 10 over 40, which is 1 over 4. Then I equals to square root of 1 over 4, which is obviously 1 over 2, or 0.5 amps. That is the current that enters through X, resistor X. However, that is not where we are going to, but we need it. Why? Because by Ohm's law, we know that what V equals to IR. So if I get the current that enters through the resistor X, I can get the voltage. Obviously, that means that my voltage is going to be 0.5 times my 40. That is going to be what? That is going to be 20 volts. That is the total voltage drop around X is what? Is 20 volts. This is not still where we are going to. Why do we need this voltage drop? Because we know this is a parallel circuit, and in a parallel circuit, the voltages are the same in a parallel circuit. So it means this same 20 volts up here in X will still be the same 20 volts in Y. So what do? We say, therefore, voltage drop at Y equals to what? The same 20 volts, because it is a what? It is a parallel circuit. Once I get this voltage drop, then I need to get the current around what? Y. So I of Y is equals to V, that is 20 all over Y, which is 60. And this is what? This is 1 over 3, or 0.33 amps. That is the current through what? Through the Y. We need the power in Y. Don't forget, power is equal to what? IV. Power is what? IV, or you say I squared R. So power of Y is equal to IV, which is IY now, because, sorry, I times V of Y, which is still the same voltage across X. And this is 0.33 times 6, sorry, beg your pardon, IV, 0.33 times 20, because it's the same voltage. And this is going to be what? Power of Y equals to, let me press my calculator, 0.33 times 20, and that is what? 6.6 watts. That's 6.66 watts, approximately 6.67. So the approximation error happens there, so we have to correct that. Times 20, that is 6.67 what? Watts. Don't forget, the unit of power is what? Is watts. And the next question, question 22. Which of the following is not a fundamental SI unit? Which of the following is not a fundamental SI unit? A, meter is a fundamental SI unit. B, ampere is a fundamental SI unit. Kelvin is a fundamental SI unit for temperature. D, second is a fundamental SI unit for what? For time. Then E, radian. Radian is used to measure angle, but it's not the only unit we can use to measure angle. We can use what? Also radian. We can use minutes. They use minutes to what? To measure angle. Minutes, seconds to measure angle. So the E is the wrong one there, or is the one that is not fundamental. Every other one is fundamental except radian. So E is the correct option for 22. Next. Question 23. A simple pendulum with a period of 2.0 seconds has its length doubled. Its new period is what? So we want to see the relationship between the period of a simple pendulum and what? And the length. So let's quickly take a look at this formula of a simple pendulum. Alright, so we have the period of a simple pendulum is simply 2 pi square root of L over G, where L is the length of the pendulum and G is acceleration due to gravity. And you can see in all of this formula, what is constant? 2 pi is constant, G is constant, because acceleration at any particular place on the surface of the earth is constant. However, it might vary from places to place. So we say that T1 all over T2 is equal to what? Root L1 all over what? L2. That's this one will make it easier for you because all other things are constant, so we can leave them out of the what? Out of the equation. So the first period is T1. So T1 was given as 2.0 all over T2 is what we are looking for. However, what happens? Equals to square root of L1. Our L1 is the initial length. Let's call it L. And 2, the L2 is now what? Is double. Don't forget, the question says it is double. So 2L, that's the meaning of L2. It is double. That's double of the initial L. And what do you have there? L cancels L. And you have 2 over T2 equals to square root of 1 over 2. And what happens? Square root of 1 over 2, that is T2 equals to root 2 over 1 times 2. Or you say 2 root 2. So what is 2 root 2? Let's press that and get the answer. 2 root 2. And that is 2.83. So the correct option is D, 2.83 seconds. That's the new period. And that is it. Next question. Alright, so question 24. Which of the following statements are true about the spring balance and the chemical balance? Spring balance are used to measure your weight. It can also be used to measure masses. However, chemical balances are only used to measure masses. And another name for them is what? Is beam balance. Beam balance. So let's go. 1, both are used to measure the mass of an object. Yes, you can use both to measure the mass of an object. That's correct. 2, either of them may be used to measure the weight of an object. No, because only spring balance can be used to measure the weight of an object. Chemical balance can never be used to measure the weight of an object. So we use it only to measure the mass of an object. 3, the spring balance works on the principle of Hooke's law. Yes. Why the chemical balance works on the principle of moment? Yes, that's also correct. So 3 is correct. 4, a change in gravity changes the reading of a spring balance. Yes, but not that of a chemical balance. Yes, because the weight, when something measures weight, it has direct relationship with what? With acceleration due to gravity. Don't forget that weight is mass times acceleration due to gravity. And this acceleration due to gravity we're talking about is not constant in all places on the surface of the earth. It varies from the equator down to the poles. Maximum at the equator, minimum at the what? At the pole. So 4 is also correct. So the correct option is going to be 1, 3, and 4. So let's take a look at them. 1, 3, and 4. Oh, we are lucky. That's the first option. Then let's move on. So A is the correct option for question 24. Next. Which of the following is not a force? Which of the following is not a force? Don't forget what a force is. A force is that which tends to change the motion of a body or the state of a body. So let's take a look at that. Friction, yeah, friction is a force. Tension is a force. Upthrust is a force. Weight is also a force. The only thing that is not a force here is what? Is impulse. Because we define impulse as what? As the product of mass and velocity.